Hello and welcome back. So now that you have the Perlin Noise 2D implemented, Lee, what do you have planned in this video?
Well, in this one, I want to play around with it. We've got value noise. We've got it looking all right. It was kind of rough because we're using a very low texture size,
Hmm.
as well as the fact that we're only using a single octave. We're not even getting the multiple octaves that we were messing with before. But what I wanted to also do is compare it with our value noise from before to get a feel for how fast Perlin noise is compared to our implementation of value noise and
Okay.
point out a couple of things. So I commented out our Perlin noise and I brought back in our value noise and I set it up to be the same x divided by 2. So we're kind of getting something comparable. Then I'm going to do the plus 1 divided by 2f so that it'll be in the right number domain. And I want to run up and look at our texture size. We're at 16. Let's try 48. A little bit higher res and see what happens. So, because I was seeing the times when we did the Perlin noise at 0 milliseconds to calculate.
Right.
It makes it kind of hard to compare numbers then. So let's go ahead and jump back into Unity. Now this should be our 2D value noise. And we're running at about half a second to generate that, which isn't too bad, but it's only one octave of 48 by 48.
Hmm.
So I'm trying to, yeah, there we go. Thank you. Now, if we take the same thing, comment out, see, we're also at a tenth of a second. I might want to change this a bit. Let's jump it up to 1 full second. So less than 1 millisecond. Sometimes it hits a millisecond for the same noise. So it's a bit faster. But just to be sure, because I did have the numbers fairly low and I did adjust, the iteration plus equals here. I want to check our timer. We're at a quarter of a second. I also want to set this to once a second because I want to make sure that everything is on the up and up between the two. So everything, let's leave this one. That's not taking effect until we do 3D anyways. But I do want to make sure that we're not overrunning the time on our update. So let's do, just to be safe, 1 minute. And we'll compare both noises on the same platform. So once again, just to make sure, because somebody will come back and go, yeah, but you changed something before you did it. So yeah, it does affect the number a little bit. So 305 milliseconds.
Wait a minute. Which one did you just run?
This one is value noise.
Yeah, I know it was value noise. Hop back over to code.
Mm-hmm.
Okay.
Yeah, I switched it, but I wanted to have a unified platform for both of them.
For some reason, my brain told me you'd gone up 2 lines to the
Ah,
3D.
gotcha. All right, but nope, that's value noise. And then if I go back, this should be Perlin. So zero point 0.5 or 5 milliseconds as opposed to 300 and something. So substantially faster. Now, if I go back into code, so yeah, we're still at texture size of 64. Let's compare what happens when we start bringing out the iterations again, or not so much the iterations, but running through multiple octaves. So I'm going to uncomment that. I'm going to copy no, not that. I want to copy both these lines. I'm going to paste those here. Comment out this one. Bring this one out. Comment out this one. This will be plus equals, and I need to comment out this one. All right, so what we're doing is we're going to run the test of value noise at 8 octaves in depth and get a timer for that, and then we'll come back and do the same thing for the Perlin noise. So if I run it, now this one should take a little bit longer. So we've completely blown it out, which means I've missed something. Count. Oh yeah, probably help if I average the numbers out. Let's try that again. All right, so 2 seconds, 45 or 455 milliseconds for 8 octaves of value.
Mm-hmm.
Now, if I go back and we do the same thing, but this time against the Perlin noise, and we run it, we end up with 10 milliseconds. So a bit faster. Now, the nice thing is, go back over to code, if I can get there. Let's go ahead and ramp up the size of our texture. I think I'm using a 256 texture by default.
Yeah, I think so.
Yeah, I think so for this size. Well,
Mm-hmm.
easy way to find out. Noise text, yeah, 256. So this one won't have any upscaling. So at 256 by 256, 165 milliseconds. Not bad at all for 8 octaves of noise.
So that's very white, or very static looking.
Right.
Okay.
Wow, we got a lot of stuff open.
You're on your computer.
Oh, yeah, I got a lot of stuff open.
There you go.
There we go. It's like, wow, I got all kinds of stuff open. All right, so now part of that is I didn't divide by I. So I'm running a lot of iterations over itself.
Mm-hmm.
So good catch on that one. So now we should have our octaves each getting a little bit more coarse along the way. So if I run value noise, give it some time to think. And some more time. And some more time. So how's the weather over there?
Apparently not as cold as it is out where you're at.
Yeah, not happy about that. But I think we're actually going to make it up into the 50s tomorrow.
Oh, well, that's good.
Yeah. It beats this 30s. So, wow. And don't worry, it's not broke, I don't think. It's just calculating 256 by 256 at 8 octaves of depth.
That will be around a minute or better.
Yeah, about that. I think when we were running it the other day, well, no, we didn't do 256, did we?
Well, we did several different sizes. I think
Yeah.
128.
See, if this goes over a minute, we might get some interesting results. It might just say, yeah, it only took 10 seconds. Because our timer doesn't take into consideration minutes. So those just get cut off. So, but we definitely can see part of the problem. So while this is going on, let's jump back over here and explain why value noise as implemented is so slow. We are using
Did you say implementate it? Awesome. You speak like me.
Did I?
Yeah,
Really?
I think so.
It's not as bad as yesterday when, I said lawnmower out of nothing.
This is true.
That was, I still don't know where that came from. It's, yeah, lawnmower. Huh? Tourette's is starting to set in. But back on topic, we're using smooth noise. Now, smooth noise is going through our hash2D and sampling it 9 different times. And we've already gone through our random noise and shown that our random noise hashes aren't the fastest calculations in the world. They're not really, really dead slow, but they aren't super optimized as opposed to our regular random number generation. So when you start off with doing a hash that is inherently slow to begin with, and then you're doing 9 of those per pixel, and then you end up doing not only 9 of them there, but 4 times 9, which works out to be, 36? Something like that? Yeah, I think 36. So 4 times 9, so you're doing 36 of those. And then you go in and you do some more interpolation on top of that, and that is per pixel. And then when you start doing 256 pixels by 256, and then you times that number by 8 more, you get quite a few calculations.
Yeah.
So, matter of fact, I think we're still calculating. So we might have overdone it for our... yeah, we've gone over a minute, so that's probably throwing our number stuff off. So we
Well,
might
here,
have...
let me go ahead and pause, and we can just kill it out, bring it back.
Okay.
Okay, Lee, we're back.
Okay, we killed Unity because it was just taking too long and started it up. But what I was driving at was the fact that this smooth noise and all of the samples to our hash2D is the main culprit of our problem. So what I'm going to do, go back to Game Manager. And instead of 256, let's dial this back down. Let's go back to 32 and see what we get.
No.
What do you want to do?
128. And
You want to do...
adjust your timer delay to 120. Whoa, okay, that's fine.
I think that's one too many digits, but here, that'll be plenty. Okay, so we'll run that.
Then this will be the one that you had about a minute on.
So we'll see.
Back down to 32. Jeez.
Well, hold on. Let's pause that. Can we pause it?
It's working, man.
It's working. Well, I still think it's going to take more than a minute. But
you think so?
Yeah. But what I was going to do was go into the code real quick.
And fix it?
No, not fix it. I was just going to, just for our value noise, add another holder in there for minutes.
Yeah, fix it.
Well, this isn't really fixing it.
Okay.
Well, our noise really shouldn't take minutes to calculate.
It's all good. We'll call it whatever you want to call it.
Making it better.
Making it better.
All right, Adam Sandler.
What? No. I'm just going with the flow.
Is that what it is?
That's right.
Okay.
See?
Hey, it did work. Look at that.
You had absolutely no faith.
Yeah, but I'm not sure if that's 21 seconds or more than 1 minute.
Well, you could find out by stopping and getting that thing recompiled real quick.
All right, so we're going to run it again for fun.
You sure things recompiled?
I hope so.
I tried to sneak in a quick Control R before your mouse made it all the way up there to the play button, but I don't know.
We'll find out.
Look at that.
Yeah, 13 seconds that time. Okay, so
Gotta
that
have
seems to go
faith in
right.
me, dropping it all the way back down to 32. You should be ashamed of yourself.
But look at it. It did compile.
Yeah, it did. My control R apparently made it in there.
Yeah. So, but I mean, come on. Almost 13 and a half seconds for a 128 by 128 texture.
Yeah, it's looking pretty smooth. You gonna show me just as smooth and lovely over on the other one?
Yeah, but I'm going to show it to you a lot faster.
Works for me.
So comment out value noise. And we'll run it. I'd say that was faster.
Wow. Yeah, that's considerably faster.
So, but, you know,
Look at that big, horrible, dark splotch that runs diagonally across the bottom.
what's so horrible about it?
Just saying.
It's not horrible. That's just noise. You end up with stuff like that with noise. But no, where I was saying optimization comes into play. If
Yeah.
you were to get rid of the smooth noise, that would help speed it up tremendously. Won't look as good, but you could do it. Another place that you could get rid of or optimize instead of using smooth noise, which relies on the hash 2D method, is you could use a lookup table for random values, kind of like what we're doing with Perlin noise. So you could do something like that as well. That would help speed it up. But in my tests that I've done with value noise, even doing that with implementing, particularly with the 3D, I haven't tried it with the value noise. Probably would come fairly close for 2D value noise as Perlin 2D. But when you compare Perlin 3D with value 3D, you don't get the same performance. Value would still run slower than Perlin or Simplex.
Well, how's the quality look with the value 2D when you start stripping some of that out and using a lookup table?
Um, it looks pretty much like random noise at that point, even with 8 iterations of noise on it. It just looks like noise on top of noise on top of noise without the smoothing and the blending across.
So the
Because
quality is not as nice looking.
right, because we're at value noise instead of a gradient noise,
Right.
so it's not smoothing out across a large distance. So you have to take that into consideration when you start looking at using a lookup table,
Hmm.
because you're going to have to find some way of sampling and then blending across those samples, which is the whole point of smooth noise. So if you were to take out smooth noise and use a lookup table, and actually I can do that to demonstrate it real quick because it's not very hard. Basically, I take this information, or my random hash 2D, and up here where we're doing our sample noise, I just replace this, and then I give it our seed. So I can use something like 20 comma. And I need to roll these down to floats. All right, so that should make everything happy. This is kind of going to simulate what you would get with a lookup table, but we're still using the hash2D method. It's just giving you a random number
Hmm.
based off position. So this would be something similar to a lookup table, just not quite as fast. But there's not that much of a performance difference between the two. But there is a great difference in performance between just calling the hash 2 or the hash 2D and the smooth noise.
Hmm.
So if I go back to Game Manager, we go back to the value noise, and
I think
go
you might be
back.
still running. Yeah.
Yeah. Want to hit Control R?
Hey, you should be good. Go for it.
All right, let's see what happens. So So 1 second, 53, or 1.5 seconds. So we essentially shaved off 12 seconds off of our generation time. But is that value noise? Or yeah, that should be value noise because I'm not using the lookup table. So, wrong one. I'm back on my computer. Don't mind me, folks. I have a hard time telling one set of icons from the other. All right. All right, yeah, we're definitely at value noise. So with the hash 2D, it is scaling because our hash 2D is designed to look that way. But when I was looking up our lookup table, it looked like we were just pulling from straight noise.
I didn't think it looked bad at all.
No, no, no. That's the hash 2D part. What I was saying that is when I just used random numbers coming in from a lookup table,
Mm-hmm.
what I got looked similar to if it was just random noise.
Wait, but your hash 2D is just giving you random. I thought we could do a good job of simulating random numbers from a lookup table with
Well,
hash
it's
2D.
it is pulling up numbers, but the difference. Can I do it? I might be able to do it real quick. Let's see. Now we've got Perlin noise 2D. So if I take these here and let's go to value noise. This is why this video is called playing around. We can play around, see what happens. All right. So if I take these. And oh well, I named those wrong. Come on, Control Z, Control Z. All right. NL, NL, NL. So take those, comment these out. So, but instead of pulling these down to 512. And because this will return a number between 0 and 255, and I want a number between 0 and 1, I can divide these by 255. So that gives me 0 to 1. And then to go from, so do I need to do -1 to 1 on these ones or not? No, I think I can do that with just 0 to 1. All right, so these are using our tables for lookup, and we'll see what happens. And
To the right. There you go.
yeah, I say that didn't look right.
No, that broken.
Out of range. Why did I end up out of range? I and J. Never mind. Because I didn't take those. And do var I equals I masked with 255. Because these numbers are not limited to 0 to 255. And all right, let's see what that is. Might work, might explode. No guarantees, no promises. Well, there's some noise there.
Like a lens flare.
Yeah, that's kind of an interesting effect. But you can see it's pulling numbers, and then each iteration is getting a little bit smaller. It's almost kind of artifacting from. Wow. Okay, come on. Mouse can work. So this one. I'm trying to think of my next move and how I'm going to adjust stuff. So these are shooting. All right, so when I do random hashes, my hashes should come back at so hash 3D divided by 2. So these are -1 to +1 space. And what are they coming back as? Oh, wonder if that's got it. Because I'm adjusting the space a second time. Because now I'm sending in a different type of information into my lerps. Well, now I'm middle gray. But it is sampling information. It's just not doing a very good job of giving me random numbers or interpolating between them. Wonder what I get out of one iteration now.
Well, how about I do this? Let me pause it for a second. I'll let you just play, and then
Okay.
we'll come back. Hang on. Let me go ahead and jump over here. One.
Okay.
Okay, Lee, it's back recording.
Yep. All right. Off camera, Jason and I have spent, the last hour or so playing around with a whole bunch of different stuff.
No, you were playing around with stuff. I was just
Yeah,
questioning you.
watching, side seat driving, making comments, the usual stuff. All right. A couple of things in our extensive off-camera testing session. Welcome to R&D, which is why we're doing it this way, is we modified where our timing is being taken place. Before we were starting our timer before we called update noise and ending and calculating the elapsed time after the update noise. What we found out while we're doing a bunch of other tests is every so often the process of setting the pixels and applying the texture was causing a hitch in the timing. And when we're starting the time, animated sequences of the noise that was becoming problematic. So what we did is we moved the start time inside of the update noise function, and we also moved the end time and calculation after we calculate the noise, but before we apply it to the noise texture. And that is yielding the same timing that we were getting before, but we're not getting that spurious hit where we're seeing about 200 milliseconds show up. So, and my dog is exploding now.
All right. That means you've probably got family coming home?
Yeah, they should be walking in the door in a little bit.
Well, hang on. We'll go ahead and pause for just a second.
All right.
Okay, Lee, we have resumed.
Again. It's a good thing we do have that pause button.
Yes, it's handy.
All right. All right. So we're other than the changes in here where we modified the timer code, the reason we went to pause a while ago, long time ago, like 3-4 pauses ago, was we were having a problem where we weren't getting the expected output. And that would be because somebody forgot to divide by 255 using the float versions of it. So I went in here and divided by 255 float, and everything started working again. So that was our initial problem. So if we go back over here, check our time, 0.25, and our 8 iterations, yeah, everything looks fine. We should be able to run. And what we should get is a blazingly fast value noise. Excuse me. Is because now our value noise is using a lookup table as opposed to even referencing the hash 2D or using smooth noise. And we do get a fairly nice noise. Now, there's a problem with this particular noise. If you look in the lower left-hand corner we're at 0, we get this little black mark. Now, we were experimenting off camera and we switched over to the 3D. We started running different iterations, and this mark just happens to exist based on values in our particular permutation table that we're using with this starting set of values. So as we switch over to the 3D and we start iterating through our Z, this black mark disappears and we get different values of noise. We also get another thing that we can't really see here until we get animated noise, which is occasionally using the lookup table is causing some, what would you call them? Almost like lines appearing, where we can see the difference in colors, almost like artifacts. So, and that appears inside of our value noise. It also appears inside of our Perlin. And then we start playing with the simplex just to verify, and they do show up in that as well. So our best guess is that it is a combination of the values that we have held in our permutation table, along with the fact that there is one commonality apart from the permutation tables, and that is the way that we're calculating which index of those perm tables to pull off. We're using this this form to pull up that information, and that's probably has some effect on when those are showing up. Now, with all of the testing we've done, we've proven that smooth noise is really, really slow. And we started testing and realized that, yeah, smooth noise does do a little bit, but not enough to justify 12 seconds of additional render time.
No.
So we scrapped that. Then we went back and we were looking at the hash 2D. Now, hash 2D shaved almost 12 seconds off of our render time, got us down to about a second and a half. A great improvement over the original. But once we put the permutation table in, we gained almost, another second and a quarter back.
Mm-hmm.
So we're down to about 38, 37 milliseconds of render time using the lookup table. So what we've done is we've grayed out or commented out our other two methods, and we've retooled our value noise to use the lookup table. We're going to leave it this way because it's the fastest implementation, and as you saw, the results aren't too bad. Actually, they're quite good for the speed that we get. Now, that being said, we also went back, commented out the smooth noise part of our value 3D noise, and we modified our lookups to use the permutation tables. Now, if you look, these are pretty much the same as these. I'm going to copy these down so you can see what's going on. So they're pretty much the same values for the first three here, but I've added an additional permutation called KK. So if you look, just like we're calculating II from the mask of I and 255 and JJ, KK is K masked with 255. We're just adding it inside of the permutation. So it's the equivalent of taking this line, hitting plus, adding another permutation, and looking up the element KK. And we're just adding that inside of each one of these values. So that's how I derived the first four. And I renamed them to correspond with what we had here, this NLLL. So those were the first four. Now the second four are the same thing, but instead of just adding the element KK, it's KK plus 1. And that gives us the second four elements. So if you want to go modify your value noise with these, you'll find that your value noise runs substantially faster, both in 2D and 3D, than it did with using the smooth noise. And we don't lose much in the way of looks, other than in the 3D case, when we start animating, you'll notice some artifacting. And we can actually demonstrate that now that I've shown you that. So if I go back to Game Manager, And I realized, I've got the same line of code here twice, one commented out, one not, so I'm going to delete that. But if I go here, I've added the value noise with the iteration. This is using our 3D version of our upgraded value noise. So if we run, then we hit play. So it should be shifting. And I'm not getting a good update, but if you look around here, here, and here, depending on the animation, you can start seeing some almost like a fault line with a separation in colors. So there's one right here. So it's lighter and then darker. And that's some of the artifacting that we're getting using the lookup tables. And we're getting that in Perlin noise and simplex noise as well. So it's got to be inside of the permutation table or the way that we're just calculating out which ones to use for our noise samples. So go ahead and pause that. But you can also see we're at about 38 seconds.
38 seconds.
Or 38 milliseconds.
That's better.
Yeah, it's all good. What's the difference? A few thousand milliseconds. So jump back in. So that takes care of our value noise. So we did label this video playing around, and that's what we did, an awful lot of it. And we ended up with a value noise that's a lot faster than it was before. Matter of fact, what we ended up with, if we compare our 2D value noise to, let's go ahead and run it. We're getting about 24 to 27 milliseconds on our 2D value noise. And when we compare that to our 2D Perlin noise, which is here.
Do you want to go ahead and comment out the value?
Yeah. Come on, we just have double noise. We don't really have Perlin 3D. I don't know how that got in there. Not at all. All right, so if we go back and we compare 24 to 27 milliseconds to 38, 39 milliseconds, we can see that there's a difference in speed, obviously, almost 10 milliseconds, a little bit over. But something else, if you look closely, is the overall look of the noise is slightly different. So value noise has its own distinct look, and Perlin noise has its own distinct look, and simplex noise has its own look. But what's kind of funny is when you look closely, simplex and value noise has looks that are fairly similar. So a lot of what you're going to end up using for your noise is going to be the look that you're going for, the speed that you can live with. If you want something that's real time, you're going to be looking at either value noise or simplex most likely. And Perlin's okay, but when you're talking about real time noise and a difference of 10 milliseconds, I'd choose something faster. So I'm trying to think. Is there anything else I wanted to show in this? We've pretty much compared all of that. We've gone through, we've updated value noise. So if you've skimmed to the end of this video, if you get past all the pausing, you want to backtrack because we did make some significant changes to the way value noise works, in addition to implementing our 2D Perlin noise and testing the speed differences between the two of them. So in the next video, we're going to start looking at the theory behind Perlin 3D, and then we'll compare that with our value 3D and look at the differences in speed that we get there.
Okay, sounds good. Well, with that, that concludes this video. Thanks a lot.